Hello everybody. So this will be the last lecture of this entire chapter, and this will be about lenses, and I will be discussing about the image formation by the type of lenses we have been discussing about, and so that's what we are going to do today. So the type of lenses that we have been discussing were convex lens and the concave lens. In fact, both of these lenses are in particular called the spherical lenses, because you have seen the interface of these lenses are actually a part of the sphere. So basically, let me show you how the refraction works. As a matter of fact, this particular topic, the mechanism of refraction, is not a part of your syllabus, though let me just give you an idea of how it looks. Let us go first to the example of a convex lens, because this is the most easiest one. So this is our convex lens. So we have here is our convex lens. Let me just name a few things. The purple line you see here, the line you see over here, is called the principal axis. It's called the principal axis. It's an infinite line. It passes through the center of this mirror, and center of the mirror, not center of the mirror, but center of this lens, this convex lens, and the center of the convex lens is the geometric center. Actually, this is the geometric center of the lens, and it's called the pole, and we just call it P. See, let me show you one thing. We have two interfaces here. One interface is this, so I can call that interface, say, let me just call this point M, this point N, and this point can be on this axis. This point I can call it Q, and over here we have R, not R, just let me use some other one. Let me call it T. So see, as you can see, there are two interfaces. One interface is this M Q N, this interface. That is one interface, and the other one is M T N. That is the second interface. All right. So basically lens is this region, this entire thing inside. So this material is actually it could be any material which has a refractive index which is different from what is outside. So whatever is inside is actually the lens material, and whatever is outside, it is some other medium. It can be anything. The outer medium can be, say, air or water. It should be transparent. That's the only criteria. And inside we can have, like, it can be anything else. It can be oil, glass, or any other material which is not this outside thing. So whatever is inside is not the one that's outside. Okay, that's just to cause a difference in refractive index. All right. So in our majority cases, we would be studying about lenses which are made up of glasses kept in air. Other Other examples or other cases are actually a bit more complicated. Not, in fact, they're not complicated. The idea we use are similar in all cases, but still it may require a big bit of experience, because mostly we are dealing with in real life air and glasses. So getting used to whatever we know is the first way to learn things. So in later or in your higher studies, you might deal with other combinations such as water, glass, water, oil, air, water, and all these combinations. So anyways, typically what I'm trying to say is the outside medium the outside medium is air, and the material of the lens is glass meanwhile. So that's enough for you. All right, now let us go into the refraction detail. So basically what happens is light is coming from the outside medium, which is the air. So light comes at whatever direction it likes. Okay, so we are not restricting at this moment, we are not restricting anything. So this is a ray of light. This blue this blue line segment is a ray of light. As it enters, as it is incident at this point, as you can see, let me mark it red so that you understand. This point on the interface MQN, this point on the interface MQN is the point of incidence, because that is where the incident ray has been incident onto. Now next question is, since the light ray has striked on the interface, how do you come to know the refraction pattern? So for that you need to apply the laws of refraction. How do you apply laws of refraction at curved interfaces? This case has been already dealt in your spherical mirror section. So similar to that, exactly similar to that, we would be dealing the case over here. So let me illustrate it in a separate figure. So let us look at the first case, at the refraction at the first interface. So let me read out the principal axis one more time. Okay, so as you can see, as a matter of fact, the interface MTN was like this, but it was a part of another sphere which goes over to this side, but that I am at present not drawing, because I am focusing on the interface MQN alone. So what happens? As you can see, this, let me just mark the point of incidence. Mark the point of incidence. The point of incidence was over here. So we had a light ray. Coming this way. Okay, what happened? Now it was incident there. At this point of incidence, we need to apply the law of refraction. How do you do that? Since this is a spherical surface, or any, let it be any curved surface, I don't mind whether it is sphere or ellipsoid or paraboloid, I don't care, but it's just a spherical surface, it's a curved surface. So what you do is, at the point of incidence, see this, at the point of incidence, let me call the point of incidence, say, I don't want to mess up with too many words, so let me just straight apply the law of refraction. What do? You first build a flat interface. How do you do that? At the point of incidence, you draw a tangent. Tangent to the point of incidence. Okay, let me use a different color so that you distinguish it properly. Okay, now we have our tangent. this this is our tangent, this is our tangent, this is our tangent. So now that is the point of incidence, that is the point of incidence, that is our tangent, and this is our the red one is the, this is the incident ray, this is the tangent to the point of incidence, this is this green dot over here is the point of incidence. Now what happens next? Now as we have drawn this tangent, we need to draw the normal to this tangent at the point of incidence. So it's a normal is actually a perpendicular line that passes through the point of incidence and is perpendicular to the tangent. So this blue line is our tangent. So this blue line is our, no, this blue line is our normal. We call it the normal. We call it the normal. This is our normal. This is the normal to the point of incidence, to the given point of incidence. Our given point of incidence was this, and we call it P. Sorry, no, we don't call it P. We call it, say, PQRST. So I would call it just E or E1. The case that E2, E3, etc. may be used to represent other point of incidences. So now what happens? This point, at the point of incidence, the light ray that was incident gets transmitted to this medium. So what is this medium? It's a glass material, so it has a refractive index, say I call it Ng, glass, and the outside medium, which was air, has a refractive index N, air. Now you know refractive index of air is always less than refractive index of glass. So what happens? The light ray, the red light ray, this light ray travels from a rarer medium into a denser medium. So what happens? The ray which was supposed to go like this happens to, it was supposed to go straight along if there were no material, but now what happens? It bends, it deviates towards the normal. Now it deviates towards the normal. So there you are, you have your refracted ray in the new medium. So at the interface MQN, at the interface MQN, we saw an incident ray. We plotted the point of incidence. We drew the tangent to the point of incidence, the interface, the flat interface, and then we drew the normal, and then applying the law of refraction, applying Snell's law, which states that when light ray passes from a rarer medium to a denser medium, it deviates towards the normal. Now there is some suspicious thing about this normal. Since this point is a point on the sphere, actually this is a sphere, but as you can see it's a two-dimension. Because it is in two-dimension, it appears as a circle, and this is the tangent on the point on a circle, and this normal is perpendicular to the tangent. What other line, what other thing is tangent to the, which is perpendicular to the tangent? What other line is perpendicular to the tangent? It is the radius. It is the diameter or the radius. So as you can see, the normal when extended into the medium is actually in fact the radius, which means the radius should end up at the center, and that center is actually the center of curvature of the interface MQN. So it is the center of curvature where this normal meets. So any normal on this interface, see on the interface, let me just highlight the interface. So our interface was this MQN. and any point of incidence on this interface has a normal which actually ends at the center of which coincides or which meets at the center of curvature of the interface. So every normal you draw, see the principal axis, the normal you draw through the principal axis actually is the principal axis itself. So it meets at the center of curvature. Every normal to the interface is in fact going to meet or coincide at the center of curvature of the given interface. So these lines are actually normal. This is I can call this normal 1, I can call this normal 2, and let this be normal 3. I mean, again, this is normal 4. In fact, normal 4 is the principal axis itself, and we have normal 5. See, normal 1, normal 2, normal 3, etc. is just my own naming. So you do not have any particular convention which this is not a law. It's actually randomly generated names. So don't think that you will have to call them any names. So it's just separate points, different normals, that's all. Anyways, the idea is that any normal you draw on this interface should pass through the center of curvature. That is the idea. So any normal you draw on the interface of the lens should pass through the center of curvature of that lens. So I hope you understand. So this makes life easy, because as you can see, imagine a light ray coming this way along the principal axis. What happens? Now the light ray is making 0 degrees, 0 angle with the normal, which means it is incident normally. We call such an incident normal incidence. Okay, when light is incident at an angle of incidence 0 degree with respect to the normal, then we call such incidence normal incidence. What happens? The light ray will make again 0 degree and will pass through the center without any deviation. So any light ray which comes through the which runs through the parallel principal axis, goes undeviated. Whereas as you see, this light ray suffers a deviation, and even any ray at any other point will also suffer a deviation. Okay, so these rays other than the ray which runs through the principal axis will suffer a deviation, and that deviation is because of the refraction, obviously, and that deviation itself is called the refraction, by the way. So let me not make you too much confused. So this is what happens at interface 1. So let us go and check what happens at interface 2. Now we are back to the second interface on the other side. So I've drawn this in such a manner because I wanted to represent that the interface Ep10 is actually a part of a bigger sphere. So I'm just trying to represent the interface as a part of a bigger sphere, and this black line is in fact the principal axis, which is the continuation from the other side. So let us go ahead and see what happens to the light ray which already has passed through interface 1. Where was interface 1? Interface 1 was actually, see, let me just sketch the interface 1. Okay, I'm not trying to redraw it here. See, this was interface 1, and you had this Q over here, right? So you have seen that any light ray which is not going through the principal axis will suffer a deviation, and that deviation subsides by the law of refraction. So what happens? The deviated ray will move through the glass medium in a straight line, so from one interface to another. What happens at this interface? At the interface Ep10. Now as you can see, at this interface again we'll have to follow the conventions. What were the conventions? See, this is the point of incidence. Now what we do next is we draw the tangent to the point of incidence. So this will, so this is the tangent. This is the tangent. Okay, so we have drawn the tangent to the point of incidence. So what happens? So let me just redraw all this without the second, without the yellow sphere, without the first interface. Let me draw everything without the first sphere. So you what you need to observe, what you need to remember is that the ray which is traveling towards the second interface is has already undergone refraction. So now it's traveling through the glass medium and then it is going into the air. Here in the first case, first interface, the light ray travel from air to the glass. Now in this case, the light ray is traveling from glass to air. So remember that, because even if I undraw this yellow sphere, you should understand this light ray is coming from glass to air, and it has already suffered a deviation, and that deviation is what is why it looks a bit slanted. Okay, it's not running parallel to the principal axis, but it is slanted because it has suffered a deviation. So let me undo all this drawing and focus on to the ray alone. So our ray was something like this. So we had such a ray. Okay, so we had a ray, and this was the point of incidence. So let me just highlight this ray with a direction. Now what happens? We had already drew the tangent to the point of incidence. So we had drawn the tangent to the point of incidence. Okay, so this was our tangent. Okay, this was our tangent. Now what was next? Let me just adjust it. Okay, what is the next case? The next case is as you can see, we have this incident ray at the point of incidence and the normal, not the normal but the tangential interface. The interface is now the tangent where we can apply the law of refraction. So by applying the before applying the law of refraction, we need to understand how the normal behaves. At the point of incidence, the normal is actually the normal to the point of incidence, and the normal is actually perpendicular to the tangent. So the normal should be perpendicular to the tangent. So that's your normal. Let me call it, say, n. Again, this normal seems to be a bit mysterious because it inside the medium, inside the glass, not inside the, actually your this center part is not inside the lens, but it is outside, because lens, as you see, ends here. We had another interface and the lens ends here, so this does not lies inside the lens, but it's outside the lens. But anyways, all you need to understand is that this is the center of curvature for this interface, the interface Ep10. So this is the center of curvature, and the normal passes normal on any point of this interface. Since this entire interface lies on the sphere, the big sphere, but it is a circle for your case, so it is a part of the sphere, and any tangent you draw to the point of incidence of on this interface, any point on this interface, any tangent you draw, and normal to that tangent will always pass through the center of curvature. They will all meet and pass through the center of curvature. let me draw a few examples. So these are the center of curve, these are the normals at various points of incidence, and they all pass through the center of curvature. So let me just erase the rest and focus on our first case. So we have this incident ray, and this incident ray is now moving from glass to air. See, glass to air means the refractive index or the optical density changes from optical density of this material, the ray which is which the interface or the material in which the ray is incident is actually has a higher refractive index as compared to the material outside. So it's like the case is light ray traveling from denser to rarer, denser to rarer. What happens according to Snell's law? What happens to a ray which travels from denser to rarer? The deviation which the light ray was supposed to the undeviated light should have gone like this, but that is not what happens. What happens is the light ray should not go towards the normal, instead of going straight, but it should be deviating away from the normal. It should be deviating away from the normal. So let me just this is the light ray without any deviation if the material was glass itself, but that is not the case. That is not what happens. What happens is the light ray should deviate away from the normal, which means it should go in this direction. So this is your emergent ray. This ray is emerging from inside the glass lens, so that is why we call it emergent ray. So we have everything together. Now we have this, we had this first in the first case. Let me just draw everything together so that you make a sense of everything. Let me put back everything together. So we had this interface, first interface. Let me erase the rest of the circle over here also. So I got rid of that. At the first interface, the ray traveled in this manner. So that was our incident ray. This is our incident ray. This is the incident ray. The ray inside is actually the refracted ray, and then the ray outside is called the emergent ray. Emergent ray. See, these namings are actually kind of useless, because at this interface, at the yellow interface, at this yellow interface, this is the incident ray, this is the refracted ray. But at the blue interface, this is the incident ray and this is the refracted ray. So it's just on a continuous manner, on a continuous fashion, we come to say this is incident ray, this is the refracted ray, and this is the emergent ray. So it's only on a continuous case, but step by step each has their own name, because as I have stated a minute ago. Okay, so that's your refraction. That's how it looks. So this is how light rays is deviated or made to deviate by this convex lens. Similarly, you can draw for the case of a light ray coming this way, a light ray coming that way. So what happens to that light? The light enters the lens and deviates a little, and then again deviates a bit more. So what happened? Light ray has deviated. So light ray on either side of the lens behaves symmetrically. So the light ray, this light ray and this light ray behave symmetrically. So any light ray equally distant from the principal axis will behave symmetrically, because we have placed the lens symmetrically, because center of the we had placed the center of the geometrical center of the lens, the pole, on the principal axis. So due to this symmetrical placement, because above and below all look same, so that's what symmetry means. All rays above, equally distance above from the principal axis, will behave symmetrically. So that's a very good thing, because that adds to our convenience. So now you can see any rays entering the lens tend to converge. That is why we called this lens a convergent lens. Now you can do the same thing for a convex lens. Concave lens. You can do the same thing for a concave lens, and I'm not going to explain everything in detail, but you can just find it out using your own ideas, because every ideas that I've been using in the convex lens applies to concave lens. The only difference is that the interfaces are curved inside. So I'm just going to put the drawing. You can analyze the situation similarly as if in the case of the convex lens. Before getting into the details, let me remind you the concave lens was actually made out of two spheres, and those two spheres are in fact like this. So the lens material lies inside this region. So this is glass, and it I have drawn it completely messed up, so my drawing is completely messed up, but just understand that this sandwiched part is the lens, and the interfaces are actually part of other spheres. Okay, so this is one interface, this is the second interface, and interface 1 is actually in fact a part of a sphere, and the second interface is also a part of another sphere, and these spheres themselves have their own centers, and that centers are the center of curvature of the interfaces. So this interface has this center of curvature, whereas this interface has this center of curvature. So they are curved around these 2 points. Just reminding you, and I'm going back to the original lens thing. That's our principal axis, the purple line. The purple line is our principal axis. P is the pole of the lens. Now consider a light ray. Just let me just go through it too fast. We have a light ray. Now it is incident at the first interface, and as you know, this is our point of incidence. What we do is we draw the tangent to that curved surface. How does that look? The tangent looks like this. Now what happens? There is a normal at the tangent at the point of incidence, and that tangent again goes through this center of curvature. Now what happens to the light ray? Where was our light ray? This is our light ray. So the incident light ray now suffers a deviation. How is that deviation? Since this was our angle of incidence and this was our normal, we call this normal, and this is air outside, and let's consider glass made lens. What happens? The light ray is supposed to not go straight, but instead, since it was moving from a rarer to denser, the deviation should be towards the normal. So the light ray is now traveling at a deviated path, and it is towards the normal, because this is the ray without any refraction, but since it is traveling in a denser medium, it should deviate towards the normal. This is going towards the normal, so there it is. Now what happens at the other interface? So at the second interface, this is the point of incidence, and at that point, the tangent looks tangent tangent looks somewhat like this, and the normal looks like this. Let me use a red color. So that is the normal there, and it also passes through the center of curvature on the other side. So we have your normal here at the second interface, the normal at the second interface. So what happens now? Where is our ray? The incident ray. This ray is the incident ray, the ray inside the lens. Now what happens? It must normally go the undeviated part. This is the undeviated part, but that is not what happens. It suffers refraction. Now it is traveling from the light ray. This light ray is traveling inside the glass and into the air. So from glass to air. Glass is has higher optical refractive index and higher optical density, and air has less refractive index, thus less refractive index, which means the light ray is traveling from denser to rarer and should deviate. See, this time the normal is not this. Okay, let me just erase that normal so that you don't get confused. Okay, you don't get confused. So this is our normal, this purple one is our normal. So what happens? The light ray, this is the undeviated light ray, and from denser to rarer means this is towards normal, but since it is denser to rarer, it should go away from the normal. And that is your emergent ray. Let me mark it with that is your emergent ray. So what happened? Overall, let me show you what happened on an overall sketch. See, you had this incident ray. It entered the glass, suffered a slight deviation, and then from there it suffered another deviation. So symmetric, again this is placed, since this is placed symmetric, the lens is placed symmetrically about the principal axis. Another ray on the other side will also behave similarly, and what happens? It goes like this and then suffers a little bit deviation, and from there it again suffers deviation. So any light ray on either sides will do the same. As you can see, no light ray is, and what happens to the light ray which passes through the pole? It goes undeviated and straight along the principal axis. So what happens? These rays, see, all the rays on this side are actually are either parallel or are at least close to one another. But on the other side, what happens? These light rays are actually, what are they doing? They are diverging away because they are going away from one another. This is going that way, this is going that way, and that way, and that way. So they are separating away from each other, and such a situation is called diverging. Okay, so this is why a concave lens is called a diverging lens. So light rays passing through a concave lens all diverge, they do not meet on the other side. But whereas in the case of a convex lens, the light ray moving through the convex lens meet on the other side and they are convergent. So you have the convergent lens and the concave divergent lens, and that's how they basically behave. Now let us study about the ray diagram for lens. Ray diagram for lens is also similar to ray diagram for mirror, but it's the phenomena, there is a difference in phenomena, and that phenomena in the first case was reflection, and in this case it is refraction. So light should go through the lens, whereas in the case of mirror, the light ray had to bounce back, reflect back. So let me just go into the details. I will be first of all I will be discussing the first principles of ray diagrams for lens, and then I will be discussing the nature of images and type of ray diagrams in each case for either of the lenses. So this is the basic setup for a ray diagram. you have your lens. See, I have drawn a rectangle here. Actually it's a cuboid, but see this this is just a representative of either lens. It can be spherically convergent and spherically divergent. That is it can be concave or convex lens. I'm just generally representing it. Okay, so you have the pole, which is the geometric center of the lens, and your lens is placed with its center on the principal axis. See, this purple line is the principal axis. I don't know what happened here. Let me just erase it. And then you have C1 and C2. What are C1 and C2? C1 and C2 are the center of curvature. As you have seen in the previous case, there were two center of curvatures. One for the first interface and the other one for the second interface. Okay, so you had two center of curvatures because these two center of curvatures lie on the either side, and they represent the center of curvatures of the two interfaces. Okay, so what comes next? Next comes measuring distances. The only distance right now available to you is this, the distance of the pole from the center of curvature. So these distances are called are represented using r, and are known as radius of curvature. You have seen this in the case of mirror. So that's it. So this is the basic setup. So now we need to develop the idea of the ray diagram. We will have to see how ray diagram works using this setup. So let me just go in. Now we have here is the convex lens. So whether be it in convex lens or concave lens, we can understand the ray diagram basically using four types of rays. See, from an object, even from a point source, you might have studied the number of rays emanating are infinite, but we do not need all those, because for any point all the rays may go to different places. So we are only interested in those rays which go through the lens. Okay, so we are only focusing on that, and that itself is infinite numbers, but we do not need that infinite number of rays. We only care about four particular type of rays. Let me show you what are these rays. Let me just draw a point source. See, in front of the mirror, see, this is this side. So basically you can divide the lens into four regions using the axis. You have two axes. Now you have this x-axis, you have the y-axis, and this is the origin. The pole is the origin. Okay, so everything on this side is, so these are conventions. Okay, remember the convention. This is the positive side, because you move towards the positive x-axis and move towards the positive y-axis, and this is the negative x-axis, and this is the negative y-axis. So this is the negative x-axis, this is the negative y-axis. So anything any position on this side, I will come to that later. So just remember these conventions. Remember that this is the you go along to the positive direction along of the x-axis here, and from here to above it is the positive y-axis. From here to the left side you have the negative x-axis, and from there to below you have the negative y-axis. Just remember this. Okay, just remember them. No need to take it for granted, but that is the coordinate system. I mean, yeah, you will have to take it for granted because that is the coordinate system that you follow. Okay, so what happens? Let me just draw a point source. You have here is a point source. Remember this. I'm going to say this once and for all, so be careful and follow this properly. If you want, you can go ahead, watch it repeatedly several number of times so that you get a grasp of this concept. So the idea is this: basically, from this point source you need to care of these particularly 4 rays. This is the ray 1. Ray 1 is the ray parallel to the principal axis. So let me just write it somewhere over here. So we have 4 rays, and these 4 rays are ray 1 you considering is ray parallel to the principal axis. I'm going to write PA in short for principal axis. So PA stands for principal axis. So you take the ray parallel to the principal axis. What happens to the ray parallel to the principal axis? Any ray traveling parallel to the principal axis will go through the other side of the convex lens. This is, in particular, I am talking about the convex lens. Any ray traveling parallel to the principal axis will go to the other side and will meet at a common point. All parallel rays traveling parallel to the principal axis will meet on the opposite side at a common point. As you can see, this is where it meets, and this point where all the parallel ray come to meet is known as the focus, and is represented using the letter F, focus. Let me tell you one more thing. The distance from pole to the focus is known as focal length and represented by small letter f. This is the focal length. The distance from pole to the focus. Focus is represented by f. So let me just write it here. You have this focus. So focus, what is focus? Focus is the point through which all the light ray moving parallel to the principal axis, or at least moving parallel to each other. Okay, any two ray moving parallel to each other will on the other side meet at a common point known as focus. See, there is a specialty about this focus, because all these rays are actually running parallel to the principal axis also. There is this principal axis, all these rays are also running parallel to the principal axis also. What happens? All these rays meet at a focus which lies on the principal axis. See, this point lies on the principal axis, and this is because and such a focus which lies on the principal axis is known as principal focus. So that's what it is. It's the principal focus. So let me just go back to the our secondary. Let me just go to the secondary. So what you need to understand is that any ray running parallel to the principal axis will go through the focus. So now you have learned about the parallel one. You learned about the ray which was the most important one, which was the ray which runs parallel to the principal axis. The second ray that you're going to consider is the ray which goes through the pole. So any ray which passes through the pole goes undeviated. It goes undeviated. So this ray which moves through the or goes through or passes through the pole goes undeviated. So that is the second ray. Second ray, let me write it down. Second ray that I am talking about is ray that goes through the pole. So that's your second ray, and that's over here. What happens to it? It goes undeviated. So you just have to draw is a straight line from the source to the pole and beyond. So that's a straight line. So that's it. Basically, these are the only two rays that you might require, but still I'm going to explain to you a few more, two more other rays. The third ray that I want to discuss with you is a ray which goes through the focus. See, as you can see, this is a lens. This is a lens. Okay, this is a lens. Any light ray running parallel on this side will go through the focus on that side. Okay, follow me. Look at the pointer cursor. Light ray from here. An incident ray is, if the incident ray is on this side, it will go through this side and move on to the focus if it is running parallel to the principal axis. So it will go through the focus. So there is a focus here. So there is a focus. I will call it F2. Why? In a minute you will know. What about, since this is a transparent material, it will pass light through this side as well as through this side. So what about a ray which comes from this side? If the incident ray is coming this way, what will happen? Symmetric to the situation in the case from this side, this ray, if it is traveling parallel to the principal axis, will go through a focus which is on the other side, and that focus, I will call that focus, and it's here, and I will call that focus F1, because here I have used C1, so I will call it F1. On this side it's C2, so I am going to use F2. So you know that there are focuses on either side, but conventionally we will be dealing with only light rays coming from left side. So there are focuses on others on the two sides, but still we are going to be using rays coming from this side. So now consider a ray which passes through the focus 1. What happens to a ray which moves through focus 1? This is the focus 1, and this is the ray, and that goes through the focus 1. Let me get rid of this focus 2 meanwhile. What happens? And also let me just erase this so that you get a clearer vision. What happens to that ray? That ray which goes through the focus will travel parallel, will go parallel to the principal axis on the other side. So this is what happens. So now the ray you have considered is the third ray, and that third ray is ray that goes through the focus, especially focus 1. So these are the three rays to go with. In fact, there is a fourth one which seems to be a bit more complicated, which I am not going to teach you. So based on these four rays, we will be drawing the ray diagram for the for this lenses. Just go through this section as many number of times as you like, so that you get a grasp of it. Similar to convex lens, we can understand the three rays for a concave lens also, which I am just going to draw it down. I will be just explaining it in brief. As you have seen, all the mechanisms that work for the convex lens applies for the concave lens as well. So what I'm saying is, I'm just going to draw all those three rays: the ray parallel to the principal axis, the ray passing through the pole, and the ray passing through the focus 1 for the case of concave lens also. But I'm not going to go in too much detail. Just take it down. You can go through the details of it in the textbook. You must read the textbook, NCRT obviously, so you will get an idea of what I'm saying. So these are the three cases that I'm going to explain for concave lens. See, for the concave lens, first you have is this parallel ray, a ray which travels parallel to the principal axis. The black one is the principal axis, and the red with an arrow is the ray. It is traveling parallel, and as it enters, since this is a diverging mirror, the light ray diverges on the other side. But what happens? How does it diverge? See, it diverges as if the ray is coming from focus 1 on the other side. Actually, the light ray is coming this way, but as you can see, the diverging ray appears as if it is coming from the focus. So if you draw another ray which is also parallel, which also appear to be coming from focus 1, and this is how you define the focus of a concave lens. The focus of a concave lens is actually, in fact, this is the focus of the concave lens. But whereas in the case of convex lens, the focus was on the other side. F2 was the focus of convex lens, and F1 is the focus of concave lens. Convex lens has F2 as its focus, and concave lens has F1 as its focus, because it only appears to be coming from here. So the image is in fact a virtual one. The real image, it's not a real image, but the image is a virtual one, because it only appears to be coming from one point. Okay, so that was the first case. A ray running parallel to the principal axis will appear to be coming from F1. Moving on to the second one. The ray traveling through the pole. A ray traveling through the pole is similar to the convex lens, because it also goes undeviated. So the ray goes undeviated. Now coming to the third case, where the ray is approaching, is appearing to approach F2. See, in fact, when you shoot this light from the other side, it tends to approach. See, these are dotted lines because they are not real, but in fact it's supposed to go through F2. That's what it means. But as it enters the lens, it deviates. What happens to such a ray which tends to move towards F2? It goes parallel. To the principal axis. So a ray which tends to approach the F2 will run parallel to the principal axis. So these are the three cases. So that's how we would be using the entire ray systems to understand the ray diagram of this. And a ray diagram special notes will be sent to you via your Google Classrooms, which you will have to be downloading it from there. So I'm going to stop this video now, and we will meet again on another video, most probably, which will be the next chapter. And problem solving is a must, so you should go through your textbook, run through your exercises, do that and clear your doubts and make your concepts solid, because physics is a conceptual subject which you will have to understand and not by heart, to learn things and to understand the beautiful nature in front of you. Thank you. We will meet again on the next video.